Welcome to qnawire.
We have another steam power plant operating on an ideal regenerative Rankine cycle. So again, we have some bleed steam coming off at some point, and then the rest of it's coming out here, and then have a pump here, and then we have this coming in, and then we have a pump here to pump it up basically to the boiler pressure. And so we have heat transfer at the boiler, heat transfer at the condenser, work going in at the pumps and work coming out at the turbine. The high pressure side, why do I have 1500 there? That's not correct. Let's see here. High pressure side is at 6000. Low pressure is at 20. And then the intermediate is at 400. Let's see, what else do we know here? We know that S5 equals S6 equals S7. And then we also know that S2 equals S1 and S4 equals S3. So let's see here. At 1, we know we have a saturated liquid at 20 kilopascals. And so we wind up with an enthalpy of 251 kilojoules per kilogram, specific volume. And then we can figure out what the work done by the pump is, which is just this first pump, because we're only pumping it up from 20 to 400. We only do about 0.4 kilojoules per kilogram of work. So then the enthalpy at 2 is this plus this, so very, almost the same. Now the enthalpy at 3, again, we have a saturated liquid, and at 400 kilopascal, so we can get the enthalpy there, we can get the specific volume there, and then we can get the work going into this pump here, and that's quite a bit more because we're pumping it up from 400 to 6000. And so that we get about 6 kilojoules per kilogram. The enthalpy of 4 is then this plus this. Now at 5, let's see here. At 5, we know the temperature at 5. I did not write in down. He transferring from my notes. I get forget what some of the stuff I need. 5 equals 450 degrees C. Okay, so we know temperature and we know pressure at 5, so we can get enthalpy, entropy. Entropy at 5 is the same as entropy at 6 and at 7. So we can then get the quality factor at 6, quality factor at 7, the enthalpy at 6, and the enthalpy at 7. Now, we know that the, let's see here, energy in must be the energy flow in, must be the energy flow out. And here we're looking at the, let's see here, what are we looking at here? This is the 6, 2, and 3, 6, 2, and 3. So this is this kind of junction right here. So basically coming in there, coming in here, and coming out there. All right. So let's see here. So we have energy coming in, energy going out. And so then we can write this in terms of a ratio of compared to M3 dot. All right, set that equal to 1. And then so we have Y equals M6 dot over M3 dot. And so then we also know conservation of mass at that junction, at that combination point. And so we wind up with converting this with the dividing through by M3 dot. We get Y H6 plus 1 minus Y H2 plus equals H3. And again, Y is this ratio here. And so we can solve this for Y, and we get that, we know all these enthalpies. So we get y equals 0.146, and that doesn't have any dimensions. And let's see here. So then we can get the heat transfer in, and that's just from the entropy at 5 minus entropy at 4. And then the heat transfer out, again, we have we've bled some off, so we got to take that into account. So we bled some off here, and so we only have 1 minus y of flow here, and so we need to we need to subtract the y out of here. Again, this is just y is dimensionless thing, so we can. This is still a specific heat, specific heat transfer, but we basically have this y because of the we don't have the full mass flow here, and so what happens is that we can think about this as is in pounds, heat transfer per kilogram of fluid flowing through the turbine. And so that's why we have this y here, this minus this factor here. And we have all these values, so we can plug it in and we get the heat transfer out is about 1,676 kilojoules per kilogram, which means the net work coming out, specific work, is about 1,617 kilojoules per kilogram. And so now we can get the efficiency just as this value divided by this value. And that winds up being 37.8%.